Hey everyone, welcome back to the Chat System Design series. Today we are going to cover the complete architecture of our chat application, bringing together everything we have talked about so far. We will walk through each component and see how they work together to deliver seamless chat experience. So let's dive right into it. So this is our final design for fully scalable and reliable chat system. We can break it down into key components like load balancers, WebSocket servers, databases, service discovery, and third parties integration. So let's start first. Uh, we will have client one. Let's make it everything white. Oh, it didn't work. Let's make this quite wider. Yeah, let's see that we have client one. Also, I want to make this white as well. And we have client two. Or let's say that we have user A and we have user B. So first, the user A and user B should sending a request through a load balancer. So both of them will send the request through a load balancer. So this will be a load balancer. Let's make this white as well. And yep, let's make them quite close together. Yeah, and let's make the load balancer quite less and make it like that. Okay, this looks way more better. So the load balancer is responsible for distributing incoming traffic requests evenly across multiple servers, ensuring that no single server gets overloaded. This helps maintain consistent performance even as the number of users grows. After that, we have a service discovery with like Zookeeper. Next, the request will pass through a service discovery. Let's say discovery, which is like Zookeeper or something like that. This one, it will be managed by Zookeeper. Zookeepers help manage which services are available, making sure each request gets routed to available WebSocket servers. Next, we will have our own WebSocket servers and caching. So we'll have, let's say that we have two users. So we'll have WebSocket server 1 and WebSocket server 2. And I don't want to make it like that, looking like that, but let's just, okay, WebSocket. Let's get it WebSocket server 1. And let's copy everything here. No, don't delete. Copy this. And I want to make it like it's aligned because I like to make everything looks good, to be honest. And so we have WebSocket server 1 and WebSocket server 2. Let's make them like that. And yep. Okay. Um, WebSocket servers like WebSocket Server 1 and WebSocket Server 2 are responsible for maintaining a persistent connection with users. This connection is essential for real-time communication, allowing users to send and receive message instantly. Each server also has a cache stored frequently accessed data, reducing the need for repeated database queries and improving responses. So let's just add the cache. I will try to add the cache here. So let's make it something like this here. But let's just make it quite small. Let's have the cache for this one. Put here, and also let's copy this component and add this one here. And yeah, so everyone has its own cache right now. Next we will have a load balancer for microservices. Um, so let's just why it's Miro sometimes work in a weird way, to be honest. No, let's just make it like that. Yes, exactly. Oh, okay, this is way more better. So we have right now another load balancer. This load balancer for microservices. After handling WebSocket connections, the messages are routed to different microservices through another load balancer. This layer is critical for managing internal communication between services like messaging service, group message handler, user services, and others. After that, we have a WebSocket manager and message service. We have these two things, and we will try to talk about them. First, let's just add a WebSocket manager. WebSocket manager, and it will have a Redis database as well. Let's just change its. Let's call it. Make it Redis DB. The WebSocket Manager is responsible for maintaining and managing connections, ensuring that messages are correctly routed to the right users. The message, and also we have a message service. Let's just add another. Uh, no. We have a message service. Okay, so the message service also will have like two things is connecting to. One is a data store, like a key value store, something like that. And also it is connected with like something like a Kafka. Like let me go here. It will be connected like with something like Kafka message queue. Why? Okay. No, delete this. Okay, let's just take it from here. Um, this one will be Kafka message queue, and I will make this one quite tall because we have a lot of things will be connected to. No. Delete this. Mhm, mhm. Okay. So, as I said before, the message service processing incoming messages, stores them, and coordinates with other services to ensure messages reach their destination in real time. We have data persistence and Redis integration. The message and user data need to be stored reliably, so we use a combination of Redis and data store. Redis is perfect for fast temporary data storage like caching user sessions or messages that are frequently accessed. Meanwhile, a more permanent data store is used for long term. So we use a storage for all messages. And we use Redis to store frequently accessed data in the WebSocket manager. Um, and I will talk in the second what is the reason for using Kafka message queue. Um, no, I can talk about that right now. 1 minute. This. Um, No, I guess it's not. It's not typing. It's not typing. Okay. So also we have, I guess we have a group messages, we have user service, and we have asset server. This is the only four things are left right now. But before going through that, I need to talk about the message. The Kafka message queue is in the chat application architecture serves several key purposes, particularly in ensuring scalability, reliability, and smooth data flow between different components. First, we have decoupling services. Kafka acts as a buffer between different microservices, allowing them to work independently. For example, when a message is sent, the WebSocket the WebSocket server can place the message into the Kafka queue without waiting for other services like message storage or notification services to process it immediately. This decoupling reduces dependencies and allows each services to operate without needing to coordinate tightly with other services in real time. And will help us a lot in the status update, like delivered, sent, and opened, and stuff like that. Also, it's handling high throughput. Kafka is built to handle high volumes of data with low latency, which makes it ideal for use in a chat application where potentially millions of users or millions of messages are being sent and received simultaneously. Kafka helps ensure that no message is lost even when the number of active users spikes. Also reliable in message delivery. By placing messages in Kafka queue, we ensure reliable deliveries. Kafka can store messages temporarily until they are successfully processed by other services, such as storing them in a database or sending notifications. If a service fails, Kafka retains the message until it can be processed, ensuring that no data is lost. The fourth thing is scalability. Kafka's architecture supports horizontal scaling. As the number of users grows, more Kafka partitions can be added to distribute the load across multiple servers, allowing the chat application to continue functioning smoothly even under heavy usage. And yeah, in summary, Kafka provides a robust backbone for managing the flow of messages in the chat application. It allows a system to scale effectively, ensures messages are reliable, delivered even under the heavy load. Okay, so we can next talk about what we can talk about next. Yeah, we can talk about the group management and user service. So let's just add a new row here. And I will say user service service. Yeah, and yeah, user service. So the user service, it will be connected with first a user SQL database. User SQL DB. What else? Maybe we could have also, like, it will be connected with, should has like a Redis cache server, I guess, as well. No, DB and SQL, and also it should be connected with the cache. Let me put a cache here. A Redis cache server here. Let's say Redis DB as well. And why don't we just get this one quite here, because I want to put the group messages service here. Okay, so what are we doing? Okay, so the we have also, let's add the group message service as well. And let's say that this is the group message service. It will also be connected with Kafka. It will have a connection with Kafka. Also the group, let's say that we have, no, we can't have group message handler first, and then it will be connected with Kafka, and then this one will be connected with a group message service, and I will talk why it looks like that. Let me just put like this. Yeah, and put this here like that. And the group message service will first share work with the same Redis that the user use, and also it will have a user group DB. It will be also, I guess, a SQL one. It will be a user group DB, and it will be SQL. Okay, can I put this away, and let's put the message group here and the message service here, like something like that. Okay, let's just put them here and this one here, and let's just mm. Okay, because it looks like it has too much of data, and yeah. Okay, this, I guess this looks quite better. Let's add another row because I arrow, sorry, for the group message handler. Okay, so let's talk about the group message handler. The group message handler takes care of group messages, ensuring that messages sent to a group, to a group are delivered to all participants. The user service also manage user related tasks like fetching user details or update user preferences. It works closely with both SQL databases for user record and Redis for quickly lookups. I guess we have our last message, our last service will be the asset service. Let's put this one here. It will be the asset service. This one for like images and stuff. And let's put them here. Okay. I guess it will be connected with two things. First, it will be have a connection with the blob storage like Amazon SS3 storage, and also it will be connected with a CDN. So the asset service handles media files such as images and videos that users share. These files are stored in blob storage which is designed for large objects like media to improve delivery speed. The asset service integrates with a content delivery network, ensuring that users get quickly access to media content regardless of their location. Let's talk again about the Kafka message because I guess it plays a huge part of this application. To handle a large volumes of messages and ensure reliability, we use Kafka messages queue. Kafka acts as a buffer, managing the flow of messages between services and ensure that messages are processed even under a high loads of or if certain services become temporarily unavailable. Um, so here it is. But I guess we can first talk about the flow of the sending message. Um, right of let me think. Sending. Let me think. So it's a big design, so if you didn't understand anything, just feel free to ask to tell me about what you didn't get. But let me talk about how the messages works. So first we have the user sends a message. Let's say user A types send a message to user B in the chat application. The request is redirected to a load balancer, which ensures even distribution across WebSocket servers. We have the WebSocket servers and service discovery. The message reaches a WebSocket server that manages the connection for user A. The WebSocket, for example, it will be this one. The WebSocket server ensures the persistent connection is maintained so that messages can be exchanged in real time. And I said before, the service discovery helps direct this traffic to appropriate WebSocket server. After that, we have cache and load balancing router. The WebSocket server may temporarily store message details in its cache to ensure quick response, especially for frequently accessed data. Once processed by the WebSocket server, the messages in then routed. The messages is then routed through another load balancer for further processing by different backend services. So we are here right now. First, we have the message service and Kafka queue. The message service is responsible for handling the main logic for processing messages. The message is then is put into a Kafka message queue. Kafka's rule here is to act as a buffer and ensure that the message act can be processed asynchronously. This helps decouple the messaging components, allowing multiple services to handle different aspects of message flow, such as saving in the database or delivering it to the receiver. The WebSocket Manager also keeps track of which users are online to ensure immediate delivery when it's possible. We have the storing messages from Kafka. The message details are stored in a data store. This like a key value store, something like that. This data store might be NoSQL database optimized for storing messages, allowing users to retrieve conversation history at a later time. At the same time, Redis might be used to cache the message temporarily, making it easier to retrieve recent messages quickly without needing to query the primary data store. In terms of the delivering the messages, the message service uses a WebSocket manager to determine if user B is currently online. We use a WebSocket manager for that. If user B is online, the message is delivered instantly through the WebSocket connection to appropriate WebSocket server managing user B connection. If user B is offline, the message is stored in Redis or primary database, and a push notification is sent to alert user B about a new message. This typically done through a third-party service like a Firebase Cloud Messaging. We have the updating message state. The message status changes through the delivery process. For example, sent when user A's WebSocket server successfully process the outgoing messaging and send them to through Kafka. We have delivered. The delivered will be when the message service confirms that the message has been delivered to user B's web socket server. And there is read, and the read will be when user B opens a message. This triggers a WebSocket event. This triggered a WebSocket event to the server, which updates the message status to read for both user A and user B. These status updates are managed by the message service and are also stored in data store to keep track of each message status. Also, there is the group messages and the group service. If the message is part of a group conversation, the group message handler is used to determine all group participants. Messages are replicated and delivered to all group members, either in real time if they are online or via database and push notifications if they are offline. The group service helps manage metadata about the group, such as participants and settings. And there is also acknowledgement and caching. Acknowledgement messages are managed by using WebSockets connection to ensure messages set in real time to optimize performance. Also to optimize the performance and recent message, their status can be cached in Redis. So I guess that's it for this video. So um, this is our final architecture for scalable and reliable chat applications. We covered how load balancers distribute the traffic, how WebSocket servers maintain also, and how various microservices handle messages, user data, and media. This architecture ensures that our chat application can scale seamlessly while providing a consistent experience for users. If you enjoyed this video, make sure to subscribe and hit the notification bell so you never miss a video, and see you in the future.